Good morning, folks. Hope you are doing well. This is more or less where we left off when we met last. Let me go just so you know which slideshow we're looking at. It's the introduction to probability, in case you want to reference it back. But we talked a little bit about what an experiment is. This slideshow has some updated graphics. Um, that might be helpful. So this is just a quick experiment with flipping two coins. You can have a number of trials, and outcomes are all the different possibilities that you can have uh, with two coins. So these are the kinds of things that we looked at when we met last, and so we're gonna expand on that a little bit. Um, and we were on roughly this slide. So Um, this this says sometimes when probability problems are complex, it can be helpful to graph the situation. A tree diagram is one tool that can be used to visualize and solve conditional probabilities. So we're going to be using a tree diagram. Special type of graph used to determine the outcomes of an experiment consists of branches that are labeled with frequencies or probabilities. So very useful. It's easy to come up with a sample space when you have, for example, um, just a small number of coins. So if you have uh, two coins, for example, I think you can reasonably go through them uh, with just eliminating things you've written down. So you could have two tails. You could have a tail and a head. You can do heads, tails, and you can have heads. So so it's not a long list. But once you get to three coins, then things get more challenging, and so that's when the tree diagram comes into play. So here's an example where you might use a tree diagram. So it says Nice Parlor claims to have more than 14 possible Sundays, and their slogan is try a new one every day for 2 weeks. Two brothers visit the shop to claim they're presented with the following menu. So you can have either one or two scoops. So it's essentially like a two-sided coin here. You could have uh, one of three flavors. So there probably isn't anything easy to imagine here, but it's like a three-sided coin. Vanilla, chocolate, strawberry, and then you have another two-sided coin over here. You could have the sprinkles or the fudge sundae, the fudge sauce. And so it would be helpful to draw a diagram like this to see what all the possibilities are. So uh, if it's a binary choice, you either get one scoop or two. And then once you decide on which one of those, you have three options. And then after that choice is made, then you have two options. So uh, let me see if there's a list. So there's a list, but you could start listing them. Uh, you could do oh, oops. you could do you could do O for one, vanilla, and then rainbow sprinkles. Okay, and I'm not gonna write all of them. And then but just to give you a sense of how you would actually list them, so it would be one, vanilla, and then fudge. If we're using the listing method, we might do it that way. And the last the last one would be, two strawberry fudge. So it would be something like two strawberry fudge. And you would list all the other ones in between. Sorry about that. I keeps doing that. Um, and either way, so you can essentially just count from here how many options there are. So obviously there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 options. And going back to the problem, the question was, an ice cream parlor claims to have more than 14 possibilities. We've listed them all out. There are only 12 possibilities, so their slogan is false. Okay, so that's uh, outside of proving that it's false. I think more importantly, it's looking at the looking at the sample space. So this would be a list of the sample space. And other questions that I think are even more relevant is like how many options include, or what's the probability of choosing fudge sauce? So then you would go through all the ones that have fudge sauce, and you'd be able to count and say, oh, look, there's 1, 2, 3, 4, 5, 6 out of the 12. So then you'd be able to compute probabilities like that. Okay, to calculate the probability of a specific outcome, we count the number of times the event occurs and compare it to the total number of events. That's what we did. Uh, and actually, so this talks about the relative frequency method. I think what we did was a theoretical probability. So what I showed over here, the 1 out of 6, you know, 1 out of 6. I'm sorry, no, this 6 out of it's one half is because it's 6 out of 12. That's the probability of having fudge sauce. That's supposed to be an F. Is 1/2 because it's 6 out of 12. That's a theoretical probability. Um, I'm not I'm not keeping track and running the experiment multiple times. I'm looking at a chart and theorizing that this is how things would come out. There is a relative frequency method. Uh, let's essentially they're calling it the same thing. It's the number of times an event A occurred over the total number of events. So uh, here's a theoretical probability question. The brothers in the first example decide to try the lucky sundae where the employees of the ice cream parlor choose the sundae for them. So that's a way of saying randomness. What's the probability that the brothers will end up with 2 scoop chocolate ice cream fudge sauce? So 2 scoops chocolate ice cream fudge sauce. Well, this is one among 12 possibilities, and there's 12 elements in this sample space. I began to list them, uh, but there's only one of those is 2 chocolate fudge, so it's 1 out of 12. Okay, and that's, as I said, it's a theoretical probability. Okay, so tree diagrams can be useful in helping us to see all the outcomes for more than one event. So same kind of thing, but let's see what the question is. Suppose we roll a fair die and toss a coin and want to count the total number of outcomes. The die rolled, the die roll has six possible outcomes, and the coin toss has two outcomes. The outcomes of the die roll can occur with either outcome. And the question is, I'm not sure there's a question. I think all they're doing is showing the sample space. So that should have been the question, is what the sample space. Well, the die, you know, a die has six sides. And then once you roll the die, you have two possibilities. So you could have you could roll a one and then flip an H, roll a one and then flip tails, and so on. So this is a vertical listing of the sample space. There are obviously 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities. And again, you can ask questions about probability. Uh, let's just do one here. Let's say, what's the probability of rolling an even number? Let's just list it this way. And and rolling tails. Okay, so you can look for the ones that have an even number. So that's this one, this one. These are just the even numbers. This one, this one. So it's those, and then among those that have tails, I'm gonna put an X for them. So there's 3 out of the 12, and that answers the question. You can reduce this to 1/4. Okay, so sometimes there may be too many possible outcomes to create a tree diagram. To avoid this, we can utilize something called the fundamental counting principle. So that allows us to count without actually having to make the tree diagram, because you can imagine a die with 20 sides. Hard to imagine, but or 12 sides. I know the name of that. That's a dodecahedron, right? Um, and if so, you can imagine that you've got two dodecahedrons, so two 12-sided die, and then try to imagine all the possible outcomes. So, so rather than write them out in a tree, we're just gonna simply multiply. So if you've got a dodecahedron and you roll it, and you've got another dodecahedron and you roll it, assuming all the sides are labeled, then you actually have 144 sides. If you have a dodecahedron, and we talked about a tetrahedron, then oops, that should have been an equal sign. Well, why don't we add one more possibility? Let's say we have a two-sided coin. So that's going to be 96 possibilities. So there's a way to keep track of things without actually having to write everything out. So here's a quick example. You've got a local pizza part of the claims that they have over 100 pizza options. You can choose the size, as you can see. You can choose the sauce, you can choose the cheese, you can choose the toppings. And so you might already be computing, but it's basically we've got 3 over here times 2 times 3 times, it looks like 1, 2, 3, 4, 5, 6. And you could just multiply across. 3 times 2 is 6 times 3 is 18. 18 times 6. So what's that? 48. So 108 possibilities. That's what I'm getting. So yes, they have more than 100 pizza options. There's a computation for us. Okay, now you can also have coins that are biased, weighted coins. And so you can craft a coin that usually lands on tails for out of 5 times and lands on heads the other 1 out of 5 times. And then you can flip it again and you have probabilities that are not 50-50. And so you can ask questions like, what's the probability of landing on heads the first time and then landing on heads the second time? So getting 2 heads. Well, there's only a 1/5 chance of landing on heads the first time, and there's a 1/5 chance of landing on heads second time. So there's a 1 in 25 chance of both of those events occurring. Okay. You can also find the probability of getting 2 tails, which normally we would expect those odds to be the same, but because this is a weighted coin, there's a 4 in 5 chance of one of the things of getting tails, and then there's another 4 in 5 chance of getting tails again. So there's a 16 in 25 chance of hitting tails 2 times in a row. And of course, you could do everything else in between. And if we were to list all the possibilities, when you take this and add it to this and add it to all the other possibilities, they should add up to 1. So this is the same kind of example, so I'm just going to go on to the next slide. I'm going to go ahead and stop this recording here and then start the next slide. Show.